Welcome to Open Source Options, where we teach geospatial analysis and programming with free open source software that's powerful. Today, we are going to discuss vegetation analysis using Sentinel-2 data. We've covered a lot of Sentinel-2 data recently. I have videos on how to download it, how to visualize it, and how to calculate remote sensing indices, specifically NDVI, which you see a visualization of here. What we're going to do today is we're going to use three different images from three different times to just kind of analyze the vegetation in a region using the normalized difference moisture index, which tells us how stressed plants are based on moisture. So let's go ahead and get into that. I'm going to get rid of this image. This is just up here to have a pretty visual while I talk, and we're going to pull in the data we want to use. So let's go into the browser once this gets going, and let me show you the Sentinel data I have. So let me close this one out. We'll refresh the browser. Okay, here we go. So I have three Sentinel images here. These are for the same area. And we can see the dates. So we have 2024, June 23rd, 2023, June 24th, and 2024, September 6th. We're going to use all three of these images to calculate the normalized difference moisture index and see how we can detect plant stress from year to year or across the season. So let's start out. We're going to bring in the data we need for this in the granule folder. We need bands 11 and 8A. So we need to go find where we have band 8A and 11 both in 20 meters. So we're going to pull those two in for our first image here. And then I'm going to close down this image and we'll get it for the next two images. So we're in the granule, the subdirectory image data. We're going to go to 20 meters and we're going to pull in 8A and 11. Have some clouds there, but that'll be okay. And let's go grab it from the last image. Let's go to granule here, image data, 20, band 8A, and band 11. Now you notice I'm doing a lot of repeated tasks here. I just had to do that 3 times to pull these into QGIS, and this is where it can be very important to learn how to write code because you can automate that process, and with running your script once, you could take care of all those things at once. And we have courses, or we're going to have courses that will teach you that, so check out the Open Source Options website for more information. Okay, now, we have all of our images loaded here. What I want to do next is I want to calculate the normalized difference water index and normalized difference moisture index, NDMI, for each of these dates. To do that, I'm going to use the raster calculator. So we'll go to raster calculator here. I'm going to set up my normalized difference equation here, which looks like this, and I just need to put the bands in on either side of it. So what we're doing here is we're doing 8A minus 11. We need to make sure we do this for the same date, okay, and not for different dates. So you can see here this is 24th, 2003. And here it doesn't matter which order for the addition, the subtraction does matter. Just make sure I have bands 11, 11, 8A, 8A, minus, plus. Okay, so now we're going to save this output layer, and we'll call this NDMI, and this is going to be, let me just double check the date behind there. This is going to be 2023-0624. Okay, so let's save that, and let's click OK, and this is going to run. I'll pause while this runs. Okay, our first one is done. Let's go and calculate the second one. Raster calculator. And now we're going to do it for 2024, 623. You know, I wish that with the raster calculator, you can pull up your previous processing efforts. I haven't been able to do that. So if you know a way to reuse your raster calculator, let me know. I guess I can copy the expression. So we're going to do June 23rd, 2024, 8 minus 11 and 8 plus 11. Okay, and then we're going to do an output here, and we're going to save the same name. We're going to change the date. So it is 2024, 6/23, and let's save that. And let's click OK to run that. And again, I'll pause it while that finishes. That one is complete. Let's do our last one, raster calculator. And we'll come down here. I just like to set this up first, makes it a little easier to know what I'm doing. Okay, and then we're going to go 8a minus 11. And I'm double clicking to add these in if I didn't explain that. 8a plus 11. And this is 2024 9/20/96. 2024 9/6. So let's do this here. 09/06. Okay, and then we'll save that. And click OK to get it saved. All right, so if you want to know more about the Normalized Difference Moisture Index, just give it a search online with Sentinel-2 Normalized Difference Moisture Index. You can find out some more of the range of values and what they mean. I'll talk about it here a little bit so we can set up some symbology. Generally, what you're going to see is values that so this index, all the normalized difference indices are going to range from -1 to +1. Values ranging from negative around 0, so about -0.2 to +0.4, generally correspond to water stress vegetation, and values greater than 0.4, so 0.4 to 1, generally indicate a canopy without water stress, so vegetation that is not water stressed. And then values closer to -1, below -0.2 are going to indicate barren soil. So using that information, let's try to set up some symbology here just to see what this might look like. So let's go to single band pseudo color. Let's slide this out. Let's change our color ramp to Turbo is probably a pretty good option for this. And let's invert that selection so that we have blue as our upper value. Invert color ramp. Let's see how many classes we have here. We have 1, 2, 3, 4, 5, 6. So what I'm going to do is let's do this as an equal interval. Let's make it 6 classes so we get all of our colors included there. And let's click classify. You'll notice here that we have a linear interpolation between these points, which will be just great. And we said anything above 0.4 was going to be in good shape. So let's make this 0.4. Let's make this 0.0. Let's make this negative 0.2. And let's make this, oops, the value here, negative 0.25. That may not be our best option. Hold on just a sec here. Okay, we're going to keep the symbology like this. It may not be the clearest representation, but if we can keep this consistent, that's what we're looking for so that we can compare this across different layers. So what we're going to do here is let's go into our layer properties here. and let's go to our symbology, and let's go style, and let's go, we'll save it as the default, and let's save the style, and we'll save all of this here, and I'm just going to save this to my downloads with the other information, and I'm just going to call this NDMI, and we'll save it there, and we'll say okay. Now what we can do is for these other layers, we can load this in. So double click here, symbology, style. I'm going to load the style, and I'm going to come here. I'm going to load NDMI. I can load it from either one of these, I guess, but we saved that default style. We'll load that, we'll open, and let's load the style, and let's say okay, and then we can turn this one off and take a look here, and we can see that we have those same values. Got our thing here, so we can see we have those same values. Oh, we don't have the same values locked in place. We should have had those values be the same. I have to go in and manually adjust those, but that's okay. Oh, and maybe I need to save it there. Let's save this here, so we have those values the same, and we will save these in the downloads as NDMI values, save, and then we can come back over here to this guy, and we can open the classification from here, and now we have those values lined up, so everything will be the same. And we can go to this one here and open up the properties for the legend, or the styles, and we can load a style, and we'll browse for the file. We'll load our NDMI, open it, load style, okay, and then we'll load the values here from NDMI values. Okay, and now we have that, so we can turn these on and off. And you'll notice now, as we look at this, we have NDM. Let's just zoom in on an area maybe around here. So now we're looking at 2023, June 24th. And now we're looking at 2024, June 24th, and our values line up. So we can see that in June of 2023, there was more water stress than in June of 2024. Okay, now if we go back and we take a look at June of 2024 and September of 2024, we can see there is much more water stress here than there was previously. There's a lot more in that green and in that yellow. So look at that. So we've already been able to go through and see how the climate can be affecting vegetation both between years and within the same year. I want to show you just a couple other ways we can look at analyzing these. And we actually have a lot more power to do this when we use a programming language like Python. We can automate and compare and pull data in a little more consistently. And like I said, on opensourceoptions.com, I don't have any courses up yet, but the vision is to get those courses up and available so you can have really in-depth, professionally done courses for free on that website. So just stay tuned to that website and to this YouTube channel to see those. But let's go take a look at some histograms. Let's take a look, and we'll start. I'm going to put these in order chronologically. So we'll have the earliest date at the beginning, 2023, and we'll have the latest date at the end, September 2024. Okay, and we can turn these layers off just so they're out of our way. Now, let's take a look here in 2023 at our histogram. So we can come here, we can go to our histogram, we need to compute this histogram. All right, very well. And now we can see, actually, I can show you something here that might make this a little easier. So we can see the frequency of each pixel value in that distribution. Now, we can save this as an image by clicking this here. I'm just going to go, and just remember this, we'll go take a look at 2024, the same date, compute the histogram. And you can see we're shifted more to the left here, right? We don't have as many of those higher values, indicating that on this date in 2023, plants were, or in 2024, plants were more stressed than they were at the same time of year in 2023. And now remember this, and we'll go take a look at how things look later in the year. We can go here and we can compute the histogram, and we can see that our plant stress values have shifted even more to the left. And I think this spike here is representative of the water of that lake in that area. Okay, let's try something. I do not know if this is going to work, but we're going to give it a try and see what happens. Let's try to put these three in a virtual raster so they're all spatially oriented together. We can just flip back and forth between the bands for our histograms. So we can go to raster, miscellaneous, build virtual raster. Let's select these three inputs. Let's make sure we get them in order, 2023, 2024. Okay, let's do it this way, just like that. And let's say okay. Let's place each file into a separate band. We can keep the resolution at the average. If we resample, let's do bilinear, and let's run this. We'll keep it as a virtual file, temporary file. So let's run. This shouldn't take very long. There it is. It's closed. And let's slide this to the top. It's going to display it weird. Well, it's kind of cool. It's going to display it weird because it's displaying it as a true color image instead of, and we can actually turn it off. It's displaying it as a true color image instead of as a single band. But if we double click here and we can compute the histogram, and now we can see it for all three bands, where band 1 is June of 2024, band 2 or band 1 is June of 2023, band 2 is June of 2024, and band 3 is September of 2024. And we can see this spike in each of those images. I think that's, like I said, the area of the lake, of Bear Lake that we're looking at. And then we can see how we get stress changes from year to year and also changes seasonally. All right. And if we were to, like I said, we can get into some of the programming languages and we can calculate these histograms in there and also calculate quantitative differences between them. But this gives you a really good idea of how these things can change through time and how you can use satellite imagery to capture those changes. All right, thanks for watching. I appreciate your time. If you have questions, leave them in the comments below. And if you want to see those courses when they come out, just go ahead and make sure you check out opensourceoptions.com.